This is section 4.2 of Intermediate Algebra online video lecture series. I'm Dr. Scott Franklin. We're going to be covering in this section compound inequalities. In the earlier section of this chapter, we learned how to solve inequalities and learned, in fact, that with linear inequalities, it's almost exactly the same as solving linear equations, with the exception of the fact that we have to remember something called the flop rule, which says that if we multiply or divide both sides by a negative number, we have to change the direction or flop the sign of the inequality. Well, we also can now consider cases where we might have more than one inequality in a single problem, what are called compound inequalities. And there's different way of connecting multiple inequalities together into a compound inequality using and using or. So we're going to talk about what the difference between those two are and how we solve those types of inequalities in this section. The outline for this section includes, we're going to start with finding the intersection of sets and solving compound inequalities involving and. There's a connection between those two. Intersections and ands turned out to be the same type of problem. Finding unions of sets, and then being able to solve compound inequalities that involve or. So let's start with intersections and unions. So to begin with, let's define the following term. The union, actually let's start with intersection. The intersection of sets A and B, written as A, and then it looks like a vertical or upside down U is what it looks like. Okay, kind of like an N but without the little stem coming off of it. A intersect B, where A and B are sets. This is called the intersection of A and B. That represents a new set whose elements are common to both A and B, meaning they're included in both sets. Okay, so the set builder notation for intersection looks like this. A intersect B, by definition, is the set of all elements X such that X is in A and X is in B. Notice intersection and turn out to be connected in this way. So let me give you an example. Consider the set 1, 2, 3, 4, 5. And let's intersect that with the set 2, 4, 6, 8. Okay? The intersection of those two sets would be a new set, and it's everything that's in both of them at the same time, right? So 1 is not in both, but 2 is in both of them, and 4 is in both of them. That's the intersection of the two sets. Okay, so if you thought of, say, this as the first set, that's A, this is the second set, this is B, then everything inside here is called A intersect B, right? That's that set in there. Now, unions are different. The union of two sets, written as A union B, notice how it looks like just a big U, is the set of all elements that are members of set A or set B or maybe both sets. So in terms of like my picture that I have here, if I have A and have B, here's A, B, the union is everything over here, and everything inside. Okay, that's A union B. So in set builder notation, we'd write it like this. We'd say A union B is the set of all X such that X is in A or X is in B. And a note here, in mathematics, or means one or the other or both. Okay, or is true if both are true, right? So either A, it's in B, or it could possibly be in both of them. So using the same sets as we have above, 1, 2, 3, 4, 5, if I were to union that with 2, 4, 6, and 8, okay, the answer would be everything that's in either one of them. So 1, 2, 3, 4, 5. 2's already in there. We don't list elements in a set more than once, just the number of times it occurs, which is once. We don't include the number of times it occurs. 2 4's in there, 6 is also in there, and 8 is in there. So this is what the union of the two sets. The list of all the elements of the set. Note that intersection and can be interpreted as synonymous, and union or can be interpreted as synonymous. So intersection means and, union means or. So let's find a few more from these examples here. The intersection of these two sets would include everything that's in both of them. This has the numbers 1, 3, 5, 7. This is the numbers 2, 4, 6, 8, and 10. And there are no elements common to those two. So the answer is the empty set, which we use this notation for. The empty set. For these two sets, we are asked to find the intersection of 1, 3, 7 and 2, 3, 8. So clearly that is just the element 3. Now, how would we solve inequalities that involve and? Okay, by which I mean that you have one inequality and another. You're asking to find what set of numbers is true for both this one and this one. Right? Well, and would mean then the intersection. So here's our technique. We're going to solve each inequality separately. In this case, the first example, they're both solved. But imagine that we actually have to do the solving in some of these problems, because we will. Once we do that, we're going to graph each solution set to each inequality on a number line and take the intersection of these solution sets. So in this example here, I'm going to draw two number lines because I'm going to graph each one of these separately. And then what I'm going to do is I'm going to draw a third number line, which I will then use to write down the intersection of those two. Intersection meaning everything that is shaded or included in both of these. So if I said x is less than 3 for the first one, that graphs, if I go here, 0, 1, 2, 3, 4. Less than 3 means parenthesis, because not included, and shade all the way to the left. Okay? On the other hand, and I'm going to line these up, so this is still 0 here, x greater than negative 1, right, is a bracket and shades all the way to the right. Now look at these two lines and say which area of those two lines is shaded in both of them. Okay? And what you'll see is that it starts at negative 1. Negative 1 is included in both of these sets, it's shaded in both of these, so it's going to be a bracket here. And all the way up to 3, but not including 3, is shaded in both of them. So this is x is greater than or equal to negative 1. So the intersection would be this set right here, which I could write a couple different ways. One I could write by graphing it. The other I could put negative 1 bracket up to 3 parentheses. Or I can do the set of all x such that x is less than 3 and x is greater than or equal to negative 1. Okay? And there you go. By the way, let me say this. You could also rewrite what's inside this set builder notation. Since it's clear that we're between two numbers, we can put x bigger than or equal to negative 1 and less than 3 as another way of writing that solution. Okay, so there's 3 forms of that solution: set builder notation and interval notation, as well as the graph. On this problem, we're asked to solve the compound inequality. We're going to graph the solution set and give our answer in interval notation. So let's start with our first equation and solve it. So x minus 4 less than or equal to 2. If I add 4 to both sides, I'll get that x is less than or equal to 6. So that one's done. Do my second equation here. So this was 1. If I do 2, I will have 3x plus 1 is greater than negative 8. Subtract 1 from both sides. I'll have 3x is greater than negative 9. And then I can divide off the 3. And since I'm dividing by a positive, the sign stays the same direction. I get x is greater than negative 3. So let's graph each of these two on their own number line. So here is x is greater than or equal to 6. 0, 1, 2, 3, 4, 5, 6. So it's bracket n to the right. X is greater than negative 3. Oh, by the way, that should be less than. That shouldn't. I made a mistake. So x is less than less than or equal to 6. So it shades this way. 0, 1, 2, 3, negative 1, negative 2, negative 3. Greater than negative 3 means not include negative 3 and shade to the right. So now graph that on a common number line. So what it's going to do is go from here's 0, negative 1, negative 2, negative 3, 1, 2, 3, 4, 5, 6 is going to go from negative 3 but not including up to 6 inclusive and everything in between. Therefore our solution graphed is this one. And we're also asked for the answer in interval notation, which means it's going to go from negative 3 up to 6 inclusive. Like that. This problem is also a compound inequality, and anytime you see more than one inequality in the same problem, that is in the same line, this is assumed to be an AND, meaning that this inequality and this inequality are to be solved simultaneously with an AND in between them. But there's a shortcut for these two. The nice thing that you can do on these types of problems is to get x alone in the middle. Once you've done that, using the addition property and the multiplication property of inequalities, then you'll have it solved. So how do I get x by itself? Imagine that if you were only on half of the problem, say the left half, you would add 3 to both sides to get that x alone, right? Well, if I can add x to both of these two sides and to both of these two sides, why not add 3 to all three sides? So start with 3 less than or equal to 4x minus 3 less than 19, and add 3 to each side. Okay, I end up with 6 less than or equal to 4x less than 22. Now I'm going to divide everything by 4 to get the x by itself. Okay, that's going to give me 3 halves over here, just reducing that fraction, less than or equal to x less than 11 halves. Now to graph that on a real number line, all I got to recognize is this means that x is between those two numbers, so I need to plot those two numbers on the real number line. Here's 0, 1, 2, 3, 4, 5, 6. Here's 1, 2, 3, 4. Negative 1, negative 2, negative 3, and so forth. Okay, now 3 halves, that's 1.5. So 1.5 is right here. So I'm going to have a bracket right there because it's or equal to. 11 halves is 5.5, so that's going to be right in between here, and it's going to be a parenthesis. So there is the graph of my set, or in interval notation, it's 3 halves with a bracket up to 11 halves with a parenthesis. How do we solve compound inequalities that involve an OR? Okay, remember OR is connected with union, so we're going to do the exact same steps, except we're going to union the two graphs. So we're going to solve each inequality separately, graph each solution set on a number line, and take the union of these solutions. And remember, union means everything from both graphs. All right, so the union of, say, these two sets, just as practice here, means 1 2, 3, 7, and 8. Notice how it's everything that's in either one of those or possibly both. So if I wanted to solve a problem that has two inequalities in it but they're connected with an OR, I'm going to solve them each separately. So I'm going to start with the first one and end up with the following. Take 2x minus 5, set it less than or equal to negative 11. Add 5 to both sides. I'll get 2x is less than or equal to 6. So divide both sides by 2. X needs to be less than or equal to 3. Okay. The second problem is 5x plus 1 is greater than or equal to 6. So subtract 1 from both sides. I'll have 5x is greater than or equal to 5. And divide both sides by 5. I get x is greater than or equal to 1. Now we graph. So for the first one, x is less than or equal to 3. 0, 1, 2, 3. Sorry. Yeah. I think this should be negative 3 because notice this was negative 11 plus 5. That should be negative 6 then. And negative 6 divided by 2 is negative 3. So it actually should be less than or equal to negative 3. Negative 1, negative 2, negative 3. So less than or equal to means a bracket and shade to the left. Okay? Next one is x is greater than or equal to 1. So here's 0, 1, 2, 3, negative 1, negative 2, negative 3. So greater than or equal to 1 means a bracket and shade to the right. So if I graph these on the same number line, 0, 1, 2, 3, negative 1, negative 2, negative 3. Take their union, not intersection, but union, which means combine them all together. I'm going to have everything that's shaded on this one and everything that's shaded on this one. Okay, means both together. That's the graph of the solution. That's every number that satisfies either this equation or this inequality or this inequality. And the way that I'd write that with intervals is I'd write these two intervals together with a union between them. So this interval is from negative infinity up to negative 3, including union from 1 up to positive infinity. And that's the solution set. All right, to wrap up section 4.2, let us do a word problem, a real-life problem. Parts for an automobile repair cost $175, and the mechanic charges $34 an hour for labor. If you receive an estimate for at least $226 and at most $294, what is the time interval that the mechanic will be working on the job? Right? He's given you a lower estimate and an upper estimate, so somehow he's estimated how much time it's going to take him. The question is, how much time is he estimating? That is, what is the interval of times that he is estimating? So to do this, we'll first set up what our variable is. Obviously, since we're looking at time, that makes a good variable choice. So let's let x equal the time the mechanic works on job. Now we can also set up the cost, because the cost is going to be in terms of the $175 for the parts plus $34 per hour, right? Per meaning time, so plus 34 times your amount of time that he works. And here's what we know, is that the cost is at least $226 and at most $294, which means the cost, which is 175 plus 34x, is between, meaning bigger than or equal to 226, but less than or equal to 294, right? That's the symbols we used for at least and for at most. Now we're going to solve this for x in the same way that we solved an earlier problem, that is to get x by itself in the middle. I'm going to subtract 175 from all three sides to get the x term by itself. This gives me 51 is less than or equal to 34x is less than or equal to 119. And if I divide through by 34 on all three sides, I have 1.5 is less than or equal to x is less than or equal to 3.5. So the mechanic will be working from 1.5 hours to 3.5 hours on the job, which we solved using a compound inequality. That's the end of section 4.2.